see if it helps. So, you know, I was going to say a triangle, this is not linear algebra, of course, this is geometry. But if I say a triangle is equilateral, do you guys know what that means? That word? Equilateral? It means what? Equal on all sides. Yeah, lateral is side, sideways, right? So equal sides, right? Well, isn't it true also that the triangle is equiangular? What does that mean? Yeah, so what would be the measure of each angle then? 60 degrees, right, if you're measuring in degrees, okay? So there are two things you can say. You can say a triangle is equilateral if a triangle is equiangular. Because if you have three 60-degree angles, you can actually prove in geometry that all the sides are the same size, right? You can also say only if. Now, what does only if mean? Only if means the triangle is equilateral implies that the triangle has to be equiangular, right? So if means if this, then that, right? Only if is saying if the triangle is equilateral, then the triangle is equiangular. And sometimes we say if and only if, and if we say that, then another way to say if and only if, another thing we'll do sometimes is we'll say the word equivalent statements, right? So equivalent statements would be if and only if. But like if I say something like this, I say ABCD is a rectangle, and I say ABCD is a square, are those equivalent? No, not equivalent. I guess the question is, could I say if or could I say only if? Which way do you think works? Yeah, if, right? It's a rectangle if it is a square, but they're not equivalent. You could say it's a square only if it's a rectangle, right? But so that's just language. It's logic, is what it really is. It's formal logic. But it's good to be familiar with it when you're going to start talking about mathematics, because we make these statements and then we try to prove them and make sense of them, and that's all involved. Okay. So I just thought that'd be good to throw at you guys at this point. I mean, maybe I should just kind of show you guys the schedule. You have to understand that I assigned some homework over the weekend, just 4 problems on this, right? The inverse of a matrix. But this is a topic that is extremely dear to me, in a way. When I first took linear algebra as a student, right around now is when I actually started liking the class. And I thought, oh, this is really different than anything I'd ever done in calculus. Okay? And the other thing that happened years later, so, I mean, I graduated college in 1994. So it must have been 1992 when I was sitting in your shoes right here, taking my linear algebra class. Years later, after I taught high school for a long time, went back and got my PhD, I ended up doing my research on linear algebra. And actually my PhD thesis is entitled On the Field of Values of the Inverse of a Matrix. So this is something I've studied a lot, okay? So the chance to share a little bit of it with you guys is really fun. We did some work on it, of course, last time, but I want to do more today because this section, the LU factorization, as I told you, it's kind of light. I mean, I could get through the main ideas pretty quickly. The other thing I wanted to do is I know you're going to have questions on this homework that you did, this Chapter 2 review. right? That's a lot of work. And you may need some help with that. So that's in the back of my mind. And then the other thing that's on my mind today is that this section, I think I told you guys, is the most important section in the entire book. You want to know linear algebra? Study 3.5. Okay? It uses some of the ideas we've already covered, I tried to do in depth, talking about span and linear independence. Those ideas come back into play on Thursday. But at least you can kind of see where we're going. Okay? So I'll tell you the very first exercise, remember when I asked you guys, do you want a proof question on the quiz? Here's the one I would have given you. Ready? Let's try this one. What is the inverse of, I better put a kind of a hypothesis first. So let's suppose, let A, B, and C be n by n matrices. Okay? Then my question is, what is the inverse of ABC? And then I'm going to say, justify your answer. All right, the three of you put your heads together, talk for a minute at most on this one. I'm noticing that it actually is not a perfectly worded question. I shouldn't just say n by n matrices. I should say n by n invertible matrices. Do you know what that word means? Yeah, so each one has an inverse, okay? So that's my assumption. Then the question is, what is the inverse of ABC? Now, how does this work? Well, ABC, when I say it has an inverse, what does that mean? Well, you know what I'm doing right now? I'm unpacking. Remember that phrase I used? I want to unpack this phrase here. So what does that mean? The inverse of ABC. Let's hold off of determinants because we haven't covered them yet. I know it showed up for 2 by 2 matrices. I guess if I said 2 by 2, I'd let you use that. But for n by n, determinants are really complicated. So let's stay away from determinants. Do you guys know the basic definition of an inverse? Like if I just say A has an inverse, then what we usually write is we would write A with a -1 next to it, right? It has to equal I, that's right. So when I say what is the inverse of ABC, I'm going to say this. I'm going to say if D is the matrix or is the inverse of ABC, then ABC, whatever matrix that is, times D has to equal what? I. Right? And it should also be true, by the way, that if you take D times ABC, that should equal I. All right? Now, one other thing maybe to concentrate on is this. I told you guys that you need to have this for the proof to work. You need the matrices to be invertible. So that implies that things like A inverse, B inverse, and C inverse exist. All right? I'm going to shut the camera off for another 30 seconds and see if you three can take it somewhere. The answer, D, should be this, guys. C inverse, B inverse, A inverse. That's what it should equal. Let's see how this works. If you write that down, do you see what happens now? Well, I'm going to use the associative property, which means I can move the parentheses anywhere I want. What am I going to group in parentheses? Do you see it? If you take these parentheses away from there and just group them around the CC inverse, you see that? Then the CC inverse, of course, becomes what? An identity. You see that? Then you have A, B on this side, and you have B inverse, A inverse on this side. So if I continue, B times I is just B, let's say. A times B inverse times A inverse. You see it? So that's A times I times A inverse. Now I'm not even writing my parentheses because I think you see the logic, right? You see how that works? Of course, it should also work on the other side of the equation too. Like, it should be that if I take this choice of D and multiply by ABC, I get the identity. C inverse, B inverse, A inverse times ABC. Do you see how that's going to work? That's all right? How many are with me? You guys all right? Okay. So that's, an example of a matrix property. Actually, there was a theorem in your book, but it didn't say this. This is an extension of something that was in your book. It's theorem 3.9 in your book. They had 5 matrix properties. They proved 3 of them, and then they said the other 2 are exercises. Okay. The one I'm looking at is C here. Do you see it? It's not as strong. It's not in marker, so it's not as strong. But do you see what it says? The inverse of A times B has to equal what? B inverse, A inverse. They call it the shoes and socks rule, or socks and shoes. Do you guys get that? Because if A is I put my socks on, and then B is I put my shoes on, and I want to undo it, you have to take your shoes off first, right? That's their way of remembering this. It's kind of counterintuitive. Like in algebra, you might think that it's going to be A inverse, B inverse, but it's not. You need to reverse things to get it to work out. And that's because matrix multiplication is not what? What's the word? Commutative, not commutative. So that's interesting, I think, that, of course, this property extends. If I said, find, I have 7 matrices, I want the inverse of that product, you have to reverse it when you take the inverse of each one. Okay? So there are some other properties that are proved. Theorem 3.6. The inverse of an invertible matrix is unique. Let's prove it. So, how do you prove that something is unique? Well, usually what you do is you do what's called a proof by contradiction. The inverse of an invertible matrix is unique. So, I guess the idea is you say, well, wait a minute, what if that's false? So here's what I'm going to do, guys. I'm going to say, how about I say B and C each be inverses of an invertible matrix A. Okay? So this is the proof. What is it I'm trying to show? Yeah, basically down at the bottom here, I'm going to say that B equals C. That's my goal, you know. I'm trying to show that B equals C. By the way, maybe one more thing to say about it. When I say invertible, right? Yes, it has an inverse. Maybe the other thing to say is that it is square, right? Let's say n by n, okay? Because if you have a rectangular matrix, we don't really have a well-defined inverse for that. Some people have tried to define it, but it's not the usual thing. Usually if we say invertible, we're talking about square matrices, okay? All right, so what do we do? Well, this is already unpacked. That's a math statement, right? And when Tyler gave us that, that's a math statement. Can we turn these words into a math statement? Well, sure we can. Like if I say that B is the inverse of A, give me an equation. Okay. Or you could even do it this way if you need to. I don't know which way will be better, right? And we have another equation. What do we have? C times A equals I, right? So we know that. Now we're trying to show that B equals C. We have two equations, but we don't have, well, I guess what I'd like to do is somehow relate them, right? Oh, but I can relate them. Do you see what's common to both equations? The identity is common to both equations, right? So this identity you can replace with what? Like, sure. So tell me what to write here. BA? Okay, let's do that. Now how do we get the B equals C from that? Do we know that A inverse exists? Yes, because we said it's an invertible matrix. So we could say CA A inverse on the right is equal to BA A inverse on the right. And by the way, that strategy would not have worked if I had written AB instead of BA, that wouldn't have worked. So this is where you have to put the right one in. Sometimes you have to try a few things. But now, yes, this works because I get C times I is equal to B times I, so I get C equals B, and that implies that B equals C. There's our proof. I just think the more of these that you see worked out, there's a difference between reading it in the book or working it out. You want to get good at proof, you need to practice. Ready for another? Oh, question, Tyler?
So you said that if you wrote it as AB, it wouldn't have worked out. If you wrote CA as AC, wouldn't it have worked out then?
Well, if I wrote, yeah, then it would work out fine.
Okay.
Sure, if you wrote AC equals AB, you could do the same idea. Yeah, that would have worked. Okay, next one, theorem 3.7. If A is an invertible n by n matrix, then AX equals B has the unique solution X equals A inverse B. We proved that already, but that's okay. It's a good exercise for you. Let's do it. I did it in class last time, I think. But let's do it anyways. If A is an invertible n by n matrix, then AX equals B has the unique solution X equals A inverse B. For any B in Rn. Now, I'm not sure that they wrote it the same way I did in the book. This is my notation, but I am trying to get you guys used to math notation here. So when I write that, can you translate that? The upside down A translates into for any or for all. Okay? For any. And then when I say this, B is in Rn, what I really mean is B is n rows, one column, so it's a column matrix. And what does the R mean? I told you guys that, right? Yeah, and real number entries. As opposed to what kind of numbers? Complex, right. So we will do complex numbers in this class in chapter 4. We're going to have to. But we don't need them for a while, and so let's keep it real as long as we can. Okay. So I have this famous matrix equation, AX equals B. That's the solution, right? I need to show that. So here I go. Proof. Oh, you guys probably know what to do, right? So what do we do? Well, we want to end up with what? All right, I'll put that down a few lines. X equals A inverse B. What are we given? That's one thing we're given. AX equals B. We're given something else.
A times the inverse of A.
Right. You actually jumped ahead a step. I mean, the given was right here, right? A is invertible. So let's unpack that. Since A is invertible, right, what can I say? A inverse exists. So that's maybe the first thing I needed, right? There, go ahead, Tyler.
I was going to say such that the A negative, or the A inverse is such that the A inverse times A would equal.
Yes, when I write this, that's what it means, right? So what should I do to my equation? On which side, the left or the right? On the left, yeah? A inverse AX is equal to A inverse B. That works, right? Then I get IX is A inverse B, and I times X is X, so I get A inverse B. Now, believe it or not, the proof is not completely done yet. There's one word in the proof that I haven't dealt with yet. Do you see it? In the theorem. What I showed is that it has this solution. But I need to also show that that solution is what? Unique. All right? So it's interesting. Quite often in mathematics, here's what you do. This shows the existence of a solution. Now, let's prove that solution is unique. That's kind of what I did up above, right? I was trying to show that the inverse had to be unique. And all you do is you just come up with another letter, okay? So I might say something like this. I might say, suppose y is another solution. Let's unpack that. What does that mean? That means a times y is equal to b. Right? But then what do? You do the same thing. Right? Apply A inverse to both sides of the equation. And what do you get? You get that y is equal to A inverse b, which equals x, right? So in this problem, uniqueness is pretty easy. It's the same argument. Sometimes uniqueness takes a little more work. I think in the theorem up above, it took a little more work to show that b and c were equal. You had to substitute somewhere. So again, I kind of like this section as kind of your introduction to proof. I think some of the proofs you had for homework were not as easy, necessarily. So, all right. So we're working on trace, and we want to use this sigma notation eventually. But for now, we're just playing with some 2x2 examples of A and B. So let me do this little work for you. The point was that if I say A is the matrix A11, A12, A21, and A22, then the trace of A is, well, A11 plus A22. You don't need sigma notation if you just have a 2x2 matrix. You do if you have a huge matrix. So what I'm going to do is I'm going to define B the same way, and I guess my question is, what does A times B look like? Well, it's A11, A12, B11, B22. I'm sorry, going too fast. A21, A22. Those are all A's. The B's will represent matrix B, so I could say B11, B12, B21, and B22. Now, first of all, what size matrix am I going to get when I multiply these together? It's going to be a 2x2. You might remember that what I said is a good way to do this is just name them with M's for now, and then realize that the numbers, the subscripts of the M's tell you where these things come from, right? So I'm going to represent this matrix in the following way. The first entry, it says row 1 of the first matrix dotted with column 1 of the second matrix. So that would be, if you guys follow me, A11 times B11 plus what? A12 times B21. That's right. You guys see that? The next entry, it's row 1, column 2. It would be A11, B12 plus A12, B22. Are you with me? Okay. And then, so this is going to be AB. And then if I want to represent the trace of AB, that would be, well, this first entry, A11, B11, plus A12, B21, plus, I don't know, I'll have to work it out, because I still need that entry. But then the point is, we know the trace of B, right? the trace of B is going to be what? I don't even have to write it down. What's it going to be?
B11 plus B22.
B11 plus B22. And so now the question is, if I'm asking you, does the trace of AB equal the trace of A times the trace of B? I guess the thing to do is take that binomial, A11 plus A22, and multiply it by B11 plus B22. You'd have to do FOIL, first, outer, inner, last, right? But the thing I notice is the very first thing you're going to get, A11, B11, would actually be this. So I'm starting to think, maybe. Then if you want to do the general, so this could be a proof for all 2x2 matrices that the trace of A times the trace of B is equal to the trace of AB. And then the sigma notation can be useful if you want to actually prove it for all cases. All right? But I'll let you guys work for a few minutes, and I'll be back, and then we'll talk some more. So that's a nice proof for 4, is that you can add two sigmas together and you get that. I agree. That's a true statement. Okay. 5 and 6, thoughts?
6, I first provide a counter example.
Okay.
And then I said A equal to 1, 2, 3, 4, and B equal to 5, 6, 7, 8.
Yeah?
The trace of AB ended up being 19 plus 50, which was 69, and then the trace of A was 5, and the trace of B 13.
Oh,
And then 13 times 5 was not equal to...
so it doesn't, so you're saying that that's false.
Yeah.
5 is false? Cool.
Sorry,
6 is false. Okay, let me get your matrices and verify with MATLAB here. A is what?
1, 2, 3, 4.
Love that matrix. B is what?
5, 6, 7, 8.
So you have 4 for the trace of A, and you have 13 for the trace of B. By the way, does this work?
For A.
Does that work? Nope. How about trace of A? Oh yeah, 4 plus 1 is 5. Oh, it does? Okay, so we have the command trace. So that's nice. And so now we can do trace of A times B, and it should just give, you got 69 for that? Whereas if you do trace of A times trace of B, you only get 65. Okay. So I guess 6, it was fortunate that we tried a counterexample before we went crazy with this. You could see this is, right? This is involved. This is only 2x2 matrices also that I'm dealing with. So these are the kinds of things you can do, but it takes some work. All right, so 6 is false. 4 is true. What about 5?
I didn't do 5 and 7.
You did 7?
Kind of. Like, I know what you need to do to get the, so, so when you do the transpose, so your A matrix has to be square, and when you transpose it,
Can I see? Can we put-
it's just kind of like, it's not really formally written out, so it's easier to say it.
Okay.
So when you transpose a square matrix, the diagonal doesn't change.
Right.
So the trace of A is the same as the trace of transpose of A.
Nice. So let me write that down first. First observation is that the diagonal of A is equal to the diagonal of A transpose. That's true. Okay.
And so, so when you do the trace of both A and transpose of A, they're equal.
Yes.
So when you put that in this
I mean, definitely true that when you this is the trace, right? I equals 1 to n, that's the trace. And because the diagonal's the same, that's going to be the same for either one.
Yeah, and then you can multiply the two.
I guess here's my question. Can we say what this looks like? The diagonal of A transpose. Can we say what that looks like? Now, A, what are the dimensions of A? We said it's n by n, right? So what's the dimensions of A transpose? N by n. And so this matrix that I'm interested in has dimensions n by n, right? And so if I kind of do what I did before, let's talk about A transpose. What does it look like? Well, it has some element. I'll just call it M for now. M11 up to M1n. And then down to MNN would be the very last entry. This would be MN1, right? And remember what we said is that when you're trying to compute one of these, okay, so in the middle here somewhere is MII, right? So I could say this. If the trace of A transpose is equal to the sum of the MIIs, I equals 1 to n, right? Does that make sense to you guys? What I really want to figure out now is what do the MIIs look like? What does MII look like? Well, MII is telling me take rho I of matrix what? A, and then dot that with what? So again, what does MII look like? The way you get MII, this is how matrix multiplication works. You take rho I of matrix A and you dot it with what? Column I of what?
Matrix A transpose.
That's right. Of matrix A transpose. Does that make sense to you guys? Because that's how it works. You take a row and a column. We've been doing it for a long time. Now there's an observation that you need to make, though. What do you know about column I of matrix A transpose? It's equal to rho I of matrix A. And so what we're really doing, MII is actually equal to rho I of matrix A dotted with itself. So that's interesting. What does rho I of matrix A look like? Well, it looks like A rho I column 1, A rho I column 2, all the way up to A rho I column n, right? If I take that row and if I dot it with itself, what you end up getting is this, right? AI1 squared plus AI2 dotted with itself squared. Do you see it? That's what you get. So, the trace of AA transpose is the sum of n of these things. Each one looks like that. And that's why the trace of AA transpose will equal the sum of I don't like what they wrote. They wrote AII squared. But I feel like you're going to get every element. MATLAB can help. Here we go. All right, here's matrix A, right? 1, 2, 3, 4. Let's compute the trace of A times A transpose, which you remember you get with the apostrophe. It says 30, right? So what did it do? 1 plus 4 plus 9 plus 16. Is that 30? Well, 1 plus 9 is 10, plus 16 is 26, plus 4 is 30. Yeah. So I guess I don't like the statement. I feel like what they should say is not AII, although, is that what it says? I feel like it should say AIJ squared, and it's the sum where I and j range from 1 to n. If you write AII, that's supposed to be just the diagonal elements. I feel like that's a typo. What they have. Oh, you can't see, sorry. Again, I feel like this is what they should have written. Is that what it says?
It's AII.
Yeah, they have a typo on our group work. They wrote AII, and that's not correct. This should say AIJ squared. Then we have it. One little typo changes the meaning. All right. Oh, what do you think about trace of AB times the trace of BA? Trace of A times B in MATLAB of using, oh, we did this already. This was Tyler's example, was 69. Let me do the trace of B times A. 69. Is that a proof? It's an example. But it's kind of a generic enough example that you made up that you might think it might be true. And I will tell you it is true, and I will tell you trying to prove it using the summation notation is really nasty compared to what we can do in a few weeks. So I want to stop. And I want to do something else here at the end of class rather than prove that. But I do want to go back to a homework problem that bugged all of us because we had no idea how to do it. So if you have your books, let's open up to section 2.3. It was the very last problem of the section. I'm sorry, 3.2. 3.2. Here it is. 47. Show that there are no 2 by 2 matrices A and B such that AB minus BA is equal to I2. How the heck do you show that? And the hint was use the trace. So, here I go. This is 47 from section 3.2. Let A and B be 2 by 2 matrices. Then AB minus BA does not equal I2. I want to prove that. Does not equal I, basically. All right, so how do I prove that? Well, they say, here, this is called a proof by contradiction. Suppose that this happened. AB minus BA equals I for some matrices A and B, 2 by 2 matrices. Well, then you take the trace of both sides. The trace of AB minus BA would have to equal the trace of I, right? Now on the right-hand side, do you know what the trace of I is? It's 2, because we're in 2 by 2 matrix. 1 plus 1 is 2. What about the left-hand side? Well, any ideas of what I could do?
Trace AB is minus trace of BA.
So this has to equal trace of AB minus the trace of BA, right? And I said I wasn't going to prove it yet, but I told you it's true that the trace of BA is equal to the trace of AB. We observed that today when we had the 69 and the 69. And so what do you get? You get 0 equals 2. But that's false, right? So this, okay, the way the proof by contradiction works, the contradiction shows that our original assumption is false. There are no 2 by 2 matrices A and B such that AB minus BA equals I. That's called a proof by contradiction. Some people think that proof by contradiction is kind of ugly. Like you shouldn't do it that way. You should do it more the way I've been showing you before. But I also think it's pretty powerful. And so I like to use that sometimes. All right. Well, I thought, so we're going to do a little preview of section 3.5. Okay. Subspace, basis, dimension, and rank. Okay? And I guess as the preview, I'm only going to work on this, a subspace today. Okay? And I'm going to say this. A set of vectors, I wonder if I should name the set or not. Let me think. How about I do this? A set of vectors in Rn is a subspace if you need three things really. So yeah, let me call the set of vectors, let's call it S. A set S of vectors is going to be a subspace if you have the following things. You need 0 to be an S. And guys, when you write this, you probably ought to put a little arrow over the 0. Because what does that mean? The 0 vector, right? And you also need S to be, and the word I like to use is closed under addition and scalar multiplication. So the new word, I guess, for you guys is this word closed. What does that mean? Well, sometimes I think it's helpful to look at so imagine vectors of the form A, B, 0. Here's a set. I'll call it set number 1, S1. It's the set of vectors of the form A, B, and notice I'm putting a 0 here rather than a C. Right? Now, my question to you guys is, do you know what I'm talking about? First of all, what world are we living in? R what? Yeah, this is contained in the world called R3. And so, like, my Calc 3 students would love this, right? Because then they can think about what these vectors look like. And when I say that the vector is AB0, where is it located? Somewhere on the xy plane, that's right. It has to be somewhere here. All right? Now, if you think about it, if you take some vector on the xy plane, I don't know, come out A in this direction and come out B in this direction, so maybe here's the vector I'm talking about, AB0, right? Is that closed under scalar multiplication? What that means is, if I multiply it by a scalar, will it still be in this set? And the answer is yes. It's going to stay in the plane. If you multiply by a scalar, we know what that does. It either stretches it or maybe reflects it the other way, but it's going to stay in the plane. Now, what if you take another vector in the plane? So let me draw a black vector over here. If I add these two vectors, and if they're both in the plane, will the sum be in the plane? So that means it's closed under addition. Well, you don't need matrix multiplication. You need scalar multiplication. And so that's where I was checking, is it true that, like, C, some constant, times AB0, what does that equal? Well, it equals AC, BC, and then 0 times C is 0, so that's closed, right? Oh, one last one. Is 0, 0, 0 in the set? Yeah, if you set A equal to 0 and B equal to 0. So that proves that S1 is a subspace of R3. And we'll talk a lot more about that next time, guys, okay? Subspace, plenty of other things to say. Do some reading. I'll see you guys next time.